Now we discuss the concepts of current, electricity. Children, what is a current here? The rate of flow of charge is called current. That is I is equal to Q by T. If n number of charges are flowing in a time t, then current is equal to n times of charge, that is Ne by T. Children, here the SI unit of current is ampere, and here ammeter is a device which is used to measure the current. And the current always flows from higher potential to lower potential. Then what is the potential, children, here? Yes, the potential is what actually here? The amount of work done to bring unit positive charge from infinity to a particular point is called potential. So potential can be written as work done by charge. It is, see children, like a current, potential also scalar, even resistance also scalar. Okay, don't get confused there. Okay, fine, you have to remember. The SI unit of potential is volt, and voltmeter is a device which is used to measure the potential. And even potential difference, children. What is the potential difference here? The amount of work done to move the unit positive charge from one point to another point in an electric circuit is called potential difference. Units are volt, and it is measured by a voltmeter only. Clear? Fine, children. When it comes to the resistance, what is the resistance, children, here? The abstraction given to the flow of charges by the material or by the conductor is called resistance. Mainly there are two reasons, children, for resistance. What is the first reason here? The collisions of electrons with the core of the material. And the second one, the collisions among the electrons itself. And the resistance depends on mainly four factors. It depends on nature of the material, depends on the temperature. In the case of conductor, resistance is proportional to the temperature. In the case of semiconductor, resistance is inversely proportional to temperature. And the third one, resistance is proportional to the length. Resistance is inversely proportional to the area of cross section. So if you can combine these two, these 2 points, you will get R is equal to rho into L by A. What is rho here? Specific resistance or resistivity. Specific resistance or resistivity. So here we can make a resistivity as a subject. So rho is equal to R A by L. What is its SI units are? Ohm meter, children. And here one important thing is that on which factors resistivity depends here. Resistivity depends only on nature of the material and the temperature of the material, but it does not depend on length and area of cross section. Means it doesn't depend on the physical conditions. It's very important. Okay, now fine. Now come to the conductance, children, here. The reciprocal of resistance is called conductance. Its units are per ohm, inverse, or mho, or simply Siemens. What is the conductivity? The reciprocal of resistivity is called conductivity. Its units are Siemens meter inverse. So these are the important physical quantities. Now comes to the Ohm's law, children. So in exam they might ask a question like this. So name and state the law which gives the relation between current and potential difference. What is that? Actually, it is the Ohm's law. So here Ohm's law states that the amount of current flowing through the conductor is directly proportional to the potential difference applied across its ends. That is, V is proportional to I. So mathematically we can write V is equal to IR. Children, condition. So very here, condition you should not forget, otherwise you won't get mark. What is that condition here? Yes, temperature and physical conditions should remain constant. And here is a circuit diagram for Ohm's law, children. Here 2 points we need to remember. Voltmeter always must be connected in a parallel. Ammeter must be connected in a series. Clear? Fine. Based on the Ohm's law, children, conductors are classed in two categories: ohmic conductors, non-ohmic conductors, or ohmic resistors, non-ohmic resistors. What are ohmic conductors? The conductors which obey the Ohm's law are called ohmic conductors. Example, all metals. For ohmic conductors, children, we have a VI graph and a IV graph. In both cases, we get a straight line passing through origin only. But difference is that slope. For a VI graph, the slope is resistance. Whereas for IV graph, the resistance, the slope is conductance. This is a point where some students are getting confused. The slope of VI graph will be resistant. The slope of IV graph will be conductance. Don't get confused. Clear? Fine, children. Now come to the choice of the material. Children, depends on the application, depends on the use. We will prefer a different material just based on their properties. Comes to the fuse wire, children. So whatever the wire which you want to choose as fuse wire, what are the properties of the fuse wire, children? Yes, should have high resistance, low melting point, and this fuse wire is made up of what? Lead and tin. Comes to the filament wire, children. It should have high resistance, high melting point, made up of the tungsten. And heating wire should have high resistance, high melting point, made up of the nichrome. Connecting wires usually copper or aluminum. So they should have, children, high melting point but low resistance. Why? They have to carry the current, right? Yes. And the last one is that here standard resistors. So the resistor, the materials whose resistance is independent of the temperature. So example, Constantine manganese. Is it clear? So just copy this topics. Now we will discuss the EMF, terminal voltage, potential drop, and the combination of resistors. Here is calories. Now we try to understand the concept of EMF, terminal voltage, potential drop, children. Now if you can see the cell, children, here. So when the current will flow, children, during the flow of current, children, charges will be moving. But already we know that in order to move the charges, some work must be done. Now look at it, children. Here this is external circuit. Here is internal circuit. Let us say from point A, here one charge is there, unit positive charge. In order to move this charge from point A to point B in external circuit, some work must be done. That is W A to B. Whereas inside, to move the charge from B to A, the work done will be BA. Now if we can add these two, children, you will get the total work done, right? Yes, obviously. Okay, fine. Now both sides you just divide with the charge Q. It is Q, H, Q. Now look at here. There is a work done to move the charge in external circuit. The work done by the work done per unit charge. What moving the charge in a outside in a external circuit is called terminal voltage. This is what the amount of work done to move the charge, the amount of work done per charge to move only within the circuit is actually potential drop. If you can add these two, children, you will get total work done to move the charge in entire circuit is a EMF. So what is EMF, children? The amount of work done to move the charge in entire circuit. What is terminal voltage? The amount of work done to move the charge in an external circuit. And even in other terms also we can define. So EMF is defined. So EMF is nothing but the potential difference across the terminals of the cell in an open circuit. Whereas terminal voltage is the potential difference across the terminals of the cell in a closed circuit. Okay, now fine. So with this relation we can write EMF is equal to V plus, that is the terminal voltage plus potential drop. Terminal voltage can be written as I into R external resistance. Potential drop is I into smaller internal resistance. So with this we can get an expression total current I is equal to EMF by R plus R. Children, in order to find the total current in the circuit, EMF by total resistance. And here we need to recall, you need to revise about the internal resistance. What is the internal resistance, children? Here the resistance offered by the electrolyte of the cell is called internal resistance. And here one more important thing is that on which factor does the EMF depends? EMF depends on the nature of the electrolyte and the nature of the electrodes. But EMF does not depend on the distance between the electrodes, surface area of the electrodes, amount of an electrolyte what amount of an electrolyte which is taken. Okay, but whereas, children, internal resistance depends on the distance between the electrodes, size of the electrodes, temperature of the electrolyte. Clear? Fine, children. Now come to the combination of resistors, children. So here we have a series combination and a parallel combination. When you can say that resistors are cut in series, children, so resistors are said to be in series if same amount of current is flowing. So here is a circuit diagram for a series combination. So in a series combination, current remains constant but potential is divided. So how can we calculate the total resistance? By adding all the resistances of individual resistors. If n number of resistors with the same resistance are connected in series, then effective resistance is equal to n times of R. Children, as we know that potential gets divided across the resistors, then how to calculate the potential here? This is V1 is equal to I into R1 by R1 plus R2, and the V2 is equal to V into R2 by R1 plus R2. Then come to the parallel combination of resistors. When you can say that resistors are connected in parallel, children, if current is divided and potential difference is same across all resistors, which means what here? Potential is constant, difference is constant across all resistors, but current is divided. Current is divided. Then what is the effective resistance, children? 1 by Rp is equal to 1 by R1 plus 1 by R2. This also can be written as like this. Rp is equal to R1 R2 by R1 plus R2. Children, a parallel combination, current gets divided. But how to calculate the I1 and I2? Look at here. So I1 is equal to I R2 by R1 plus R2. I2 is equal to I R1 by R1 plus R2. If n number of resistors with the same resistance are connected in parallel, then effective resistance is given by Rp is equal to R by N. Now come to the electrical energy. Children, electrical energy is the most desired form of energy. But how to calculate that? Look at here. For suppose the resistor R is connected to the battery of voltage V, so that current I is passing in a time t. Then electrical energy. So electrical energy we can represent with a W. Don't get confused like a work. Don't think it is a work. So we can use actually. So W is equal to V into Q, and we know the Q is equal to I into T. So W is equal to VIT. From the Ohm's law, we know V is equal to IR. Then we will get I square RT. And by simplifying, we also get W is equal to V square by R into T. Clear? Fine. What are the essence of electrical energy? Joules only. But commercial units of electrical energy are watt hour and kilowatt hour. 1 watt hour is equal to 3600 joules. 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. Next, electrical power, children, means the rate of supplying of power, the rate of supplying of energy, or the rate at what rate electrical appliance can consume the energy is also called as a power. So power is equal to electrical energy by time. Okay, means in all these expressions, if you can divide with the time, children, you will get the expressions for the electrical power. Children, here power rating of electric appliance is very important. So what information do we get from the power rating of an electric appliance? Yes, by knowing the power rating of an electric appliance, we will come to know that the safe limit of current through a particular device, and even we can calculate the resistance of that particular appliance when it is in use. Done? Fine, children. Now children, how to calculate the electrical energy? So electrical energy can be calculated like this here. It's a power into time, but power must be in kilowatt, time must be in hours. So whatever the value which you will get, that value you will get in kilowatt hour. Children, kilowatt hour is nothing but actually it's a 1 unit actually. 10 kilowatt hours means 10 units. So hence the cost of electrical energy is equal to number of units into cost per unit. Then which we will get the amount of what you can say money which we are going to pay for the amount of electrical energy which we consumed. Now the last point in this current electricity is what actually it's a whenever, children, remember that whenever current flows through a resistor, okay, if I current passes through a resistor of R in a time t, some amount of heat is produced. That heat produced depends on current, resistance and time. Then how can we calculate that, children? H is equal to I square RT. It is in joule, but 1 joule is equal to 0.24 calories. You substitute that, you will get H is equal to 0.24 into I square RT. It is in calories. So these are the concepts of current electricity.